Okay, thanks a lot. So yeah, I'm going to talk about quantum supremacy and the complexity of random circuit sampling. I'm Bill Fefferman from UC Berkeley and the University of Maryland, and I'm very fortunate to be here today giving this talk, but clearly the work behind this talk would not have been possible without my collaborators Adam Boland, Chinmay Nurki, and Umesh Vazirani. Okay, so let's start at the beginning. The goal of quantum supremacy is to exhibit a practical demonstration of a quantum computation that's prohibitively hard for classical computers. Now, there's a few requirements. I think it's important to get them right. We need to have a task that's experimentally feasible in the very near term. We want theoretical evidence for hardness. In other words, that the problem could not be solved efficiently on a classical computer. And I'm going to demand that we're going to be reasonably rigorous about this, right? It's not just enough to show that the best algorithm that we know of for classically simulating these systems doesn't work. We really want to show that no efficient classical algorithm works. And so this is the domain of complexity theory, and that's why we're going to have to use these tools. Okay, but these two constraints are kind of challenging enough, and so just like the early days of quantum algorithms, for the time being, we're not going to need the task to be useful. Okay, so that's not the requirement. Now, quantum supremacy is an important stepping stone to scalable, fault-tolerant, universal quantum computation, but it's much more than that. Okay, so first, in a convincing demonstration of a quantum supremacy experiment will be crucial to pinpointing the foundations of computation, right? Well, we can think about it as an experimental violation of the extended Church-Turing thesis. Okay, so roughly speaking, what this means is that if we want to model efficient computation using some kind of pervasive universal theoretical model, we must consider quantum mechanics. This is a very deep statement. In particular, it means that the classical Turing machine is just not the right model for efficient computation. So of course this would complement theoretical evidence given by earlier speedups, such as the famous algorithms, quantum algorithms from the early 90s, like Bernstein-Vazirani, Simon's algorithm, and Shor's algorithm. But this would really be the first time that we've seen a quantum speedup done experimentally. Okay, and so it's really quite an important goal. We can also think of quantum supremacy as validating quantum physics, okay, in kind of a genuinely new regime, right? So, as we all know, the exponential growth of the Hilbert space is arguably the most counterintuitive aspect of quantum mechanics. And many people have asked, is this exponential description of a quantum state really necessary? Or is it just that we're ignorant of some more compressed description, right? And so I think what quantum supremacy gives us is a new limit in which to test physics, which we call the regime of high complexity. Okay, but as we've heard many times this week, in this regime, there's a really profound difficulty, okay, which is how do we classically verify something that's intrinsically exponentially complex? Okay, so we'll talk about that today in the context of quantum supremacy. Okay, and I see this, these last two motivations as being incredibly important, but admittedly a bit kind of, highfalutin pie in the sky. This one is, much more pragmatic, and maybe you haven't heard it before. I think that quantum supremacy will be important to validate near-term devices and experiments. So what do I mean by this? Well, for quantum supremacy, it seems necessary to have a large quantity of high-quality qubits. Okay, and maybe not surprisingly, achieving both quality and quantity at the same time is quite difficult experimentally. And so in recent years, tools that were developed originally in the context of quantum supremacy have become more and more central to experimental efforts in validating these NISQ devices, or near-term intermediate-scale quantum devices. So for example, we hear the Google group today talking about how they're using these tools that were originally developed in the context of quantum supremacy to, for example, tune their superconducting qubits or diagnose experimental errors. Now, I want to be really clear about this. I think this is, potentially a very important use of these tools. In fact, it's potentially a use that could outlive, the first demonstrations of quantum supremacy, right? It's something that might be useful in the future. But I think before we have a lot of confidence in these tools, we really need to understand them and how broadly they're applicable, right? So I see our work today as, an important first step in that direction. Okay, great. But if we look at existing quantum supremacy proposals, well, broadly speaking, they fall into two categories. And we're not really happy with either one at the moment. Okay? So one, there are theoretically driven proposals. These are proposed by theorists, not surprisingly. They're kind of special purpose devices with good evidence for hardness that, no classical algorithm could simulate these devices. But they're not yet experimentally feasible at sufficiently large scale to, for example, violate the extended church Turing thesis. Okay? So the one that we'll talk about a bit is the boson sampling proposal of Aronson and Arkhipov, which now dates back to 2011. And then separately, there are the experimentally driven proposals. Okay, and not surprisingly, these are proposed by experimentalists, and they kind of have the opposite behavior. They will be realizable in the near term on the path to universal scalable quantum computation. But they do not yet have as strong evidence for theoretical hardness. Okay, and so our focus today is mainly going to be on the random circuit sampling proposal of the Google and UC Santa Barbara group. And this is first proposed by this Boisho et al. Paper, which in fact appeared at last year's QIP. Okay. All right, so what do we do? So we kind of have two major results. Our first result is that we kind of mend this theoretical and experimental gap that we saw in the supremacy literature. Okay, so we provide experimental backing, theoretical backing to the leading experimental candidate for quantum supremacy, which is this random circuit sampling proposal of the Google and UCSB group. Okay? And then we study verification, clarifying when existing proposals work to verify these quantum experiments and devices. Okay, so let me start by talking about what I think is maybe the main message for this talk, which is how to obtain quantum supremacy from average case interference patterns. So what do I mean by this? What is an average case interference pattern anyway? So I guess the point is this. Quantum speedups generally come from carefully engineered interference patterns with large amounts of constructive and destructive interference. Okay. Now, in the NISQ era, okay, this intermediate scale quantum era, what we see are kind of random average case interference patterns. And I guess what I mean by that is if we were to plot the outcome probability distribution, after we say run our experiment and measure in the standard basis, what we see is that these kind of outcomes are reasonably flat. They're not so peaked like you would have to say solve to compute an algorithm from the early 90s like Shor's algorithm. They're flat. Now they're not uniform, but again, they're not so peaked. So I think with this type of average case interference pattern, the only supremacy proposal that really makes sense is to effectively have the quantum experiment try and simulate an ideal version of itself. Okay? Or more formally, given the description of a random quantum circuit, sample from a distribution close to its ideal outcome distribution. Okay? Now, closeness here is going to be in total variation distance, and let's say constant total variation distance, and it's supposed to model some form of experimental error, okay, or noise. Okay, so then our question becomes, well, how hard is this task, which I'm going to call approximate sampling, for a classical computer? Okay? Should we expect a classical computer to be able to sample from a distribution close to the outcome distribution of a random quantum circuit? Okay, so that's a task I'm going to call approximate sampling. Okay, good. So now let's dive right in. So how would we prove classical hardness of quantum sampling, or approximate sampling? So the goal is to show that there's no classical approximate sampler algorithm. And the key technical tool that we have here at our disposal is one that was developed by Aronson and Arkhipov in the context of boson sampling, but in fact it's useful more generally, which is that it suffices to prove that approximating the output probability of most random quantum circuits drawn from some distribution is sharp p-hard. Okay? So in other words, there's a reduction. If we want to show that there's no approximate sampler algorithm, then it suffices to prove that a certain problem is hard, and what that problem is approximating the output probability of most random quantum circuits drawn from a certain distribution. Okay? So now we've kind of reduced our question to showing evidence that this statement is true, okay? That this problem is sharp p-hard. Okay, great. Now this is exactly the setting of boson sampling, and not surprisingly because they developed these tools. The task is to sample from the outcome distribution of a random linear optical quantum circuit. Okay? Now, why are we talking about linear optical quantum circuits, these special class of non-universal quantum circuits? Well, the key point theoretically is that the output probabilities of random linear optical circuits correspond to permanence of random matrices. Okay? But why do we care about the permanence of random matrices? Right? Because it turns out that the permanent has a very special property, and it's not a property that we as complexity theorists see every day. It's what's called a worst to average case reduction. Okay? And so what this says is that it's sharp p hard to exactly compute the permanent of most random matrices. Okay, with respect to a random matrix ensemble. And so what this means, in other words, is that if I had a box that, could compute the permanent of most matrices, I have a reduction that says that I could use that box to compute the permanent on a worst case matrix. Okay, so it's a very special property, and we call this a worst to average case reduction. Okay. But boson sampling, despite being, I think, very appealing for a number of reasons, especially theoretically, seems somewhat hard to experimentally implement. Okay? The fact is, we've yet to see sufficiently large experiments to test, for example, the extended Church-Turing thesis. And furthermore, it's a special purpose device, so it's not necessarily on the path to universal scalable quantum computation. Okay? So what I mean is that it's not totally clear what the goal of building larger and larger boson sampling devices has to do with our kind of larger goal, which should be to build a universal fault-tolerant scalable quantum computer. Okay, great. So more recently, Google has introduced random circuit sampling. And the task is deceptively similar to boson sampling, okay? It's to sample from the outcome distribution of a random quantum circuit, right? But now what they mean by random quantum circuit is very different than boson sampling, okay? So they want to generate a quantum circuit on n qubits on a 2D lattice with, say, square root of n layers of Haar random nearest neighbor gates. Okay? Now we're going to start in the all zeros initial input state, apply these gates, and then measure in the computational basis. So this is what I mean when I say the random circuit sampling task. Let's look at it schematically. So here's one layer. Of course, we can have square root n different such layers. Okay? And the circles are qubits. The edges are Haar random, nearest neighbor 2-qubit gates. Okay? So again, I start in the all zero state, I apply square root n of these layers, and I measure in the standard basis. That's the task. Okay? Now, I want to be clear about this. I think this is interesting because it's experimentally compelling. Okay? We've heard that large systems of superconducting qubits will be coming soon, and will do exactly this task. Okay? So one example is the Google and UCSB experiment, but there are other groups doing similar things. Okay, now let's talk about theoretical hardness. So we want to conjecture a similar thing that we did for boson sampling, which is that it's sharp p hard to estimate the output probability of most random quantum circuits. But now what we mean by most random quantum circuits is with respect to this distribution that I just described. Okay? But, and again, this looks extremely similar to the boson sampling proposal, but there's one key difference, okay, which is that unlike boson sampling, there's no connection between the output probabilities of these circuits and permanence. Okay? And that's a problem because the reason that boson sampling was so theoretically compelling, right, was that it had this average case hardness property, okay? And that came from the fact that the output probabilities could be described as permanence. This is not the case anymore with random circuit sampling, and so we don't have this property, okay? At least not until we prove it, okay? So our main result is going to be to fill in this gap. We're going to show average case exact hardness for random circuit sampling. And to do this, we'll prove a worst to average case reduction for exactly computing quantum output probabilities. Okay? And what this does is it provides a rigorous foundation for the classical hardness of random circuit sampling. Okay? I think of this as raising RCS to the level of boson sampling, and even maybe a little bit more, because RCS has a provable property called anti-concentration, okay, which was not known to be true for boson sampling, although it was conjectured and probably is true, but we don't know how to prove it yet. Okay? But what I want to say is that we're not done yet. Okay? We still have a remaining hurdle, and this is the same remaining hurdle that boson sampling had, which is that eventually what we want to show is not just that it's average case hard to exactly compute the output probability, but that it's average case hard to approximately compute the output probability. And we don't fill in this gap. So we kind of raise RCS to the level of boson sampling, maybe a little bit more because we have anti-concentration, but we don't quite, solidify the classical hardness. Okay, so that's a big open question that remains for all supremacy proposals. Okay, good. So let me tell you the major ideas that we use in the proof. Okay, so our goal, again, is to get this worst to average case reduction working. What that means is that we're going to use the presumed ability to compute the output probabilities of typical random quantum circuits drawn from the ensemble I just talked about to compute the output probability for a worst case circuit C. Okay? That's what I mean by a worst to average case reduction in this context. And so a natural idea is to somehow take the worst case circuit C, that's the circuit I want to compute the output probability of, and somehow scramble it so that it looks typical. Okay? So that it looks random, so that I can use my ability to compute the output probability of a random quantum circuit to compute the worst case circuit. Okay? Here's a first attempt. Like all first attempts, this is going to crash and burn. Okay, so here's what we're going to do. Let's suppose the circuit C has M gates. Okay, then we're going to choose, independently M Har-random 2-qubit gates. Okay, we're going to call them big HI. Now we're going to take each circuit in C and just multiply it gate-wise by this Har-random gate. Okay, now we've done one thing extremely well here, right? Which is by the properties of the Har measure, we've completely scrambled the circuit, okay? We took our worst case circuit, and now it's completely average case circuit. It's completely random, okay? But we've done this too well, and that's the problem, okay? It's not clear at all how we would use information about this scrambled circuit, C prime, to somehow compute the worst case, the output probability of our worst case circuit C. Okay, so we're going to need to do something a little bit more clever. And to do that, we're going to correlate many random looking circuits with our worst case circuit C. Okay, so we're not just going to scramble, we're also going to scramble, we're going to scramble and then correlate as well. Okay, and to do that, we're going to use kind of two technical tools, which is the polynomial structure that comes from the Feynman path integral, and also the uniquely quantum ability to implement a tiny fraction of a quantum gate. This is something that we can't do classically, but we can do quantumly. It's pretty interesting. Okay, so let me just give you the vague idea about how this works. Let's consider picking many small angles, theta. Okay, you should think of these as close to zero, like inverse polynomial quantities. Now for each theta, let's consider the circuit C prime, okay, in which each gate in C prime is what we get if we take each gate in C, that's our worst case circuit, so we'll call that Ci is the ith gate of our worst case circuit. We scramble it by multiplying by this Har-random gate, Hi. Okay? Now at this point, remember, we're completely scrambled. Okay? But we're not going to stop here. We're now going to rotate by a small angle, right, in the direction of Ci, the worst case gate. So in other words, we're going to apply the gate e to the minus I little hi theta, where little hi is the log of big hi. And remember, big hi was the Har-random gate. Okay, so now what does this do for us? And this is the crucial observation that we're going to use in a very technical proof, which is that each circuit C prime now, or C prime of theta, individually looks random. Okay, we've basically scrambled it. Okay, but in fact, they're actually all correlated, right? And the way you can see this is because of the Feynman path integral representation of the output probability of a quantum circuit, we can express the output probability of each circuit C prime as a fixed function of theta. Okay, and from here we can use ideas from polynomial interpolation to recover the output probability of the worst case circuit C. Okay, now it's not at all clear, all the technical details. I kind of purposely pushing them under the rug. The reason is because I really want to also have time to cover what I see as our second contribution in this paper, which is how to use statistical tests to verify the random circuit sampling proposal for quantum supremacy. Okay, so let me tell you the challenge. We want to develop a statistical measure to verify the random circuit sampling output distribution using samples from the device. Okay. But we have some constraints. All right, so our first constraint is we don't know the output distribution of the circuit. We're not given the probabilities explicitly. We're just given a description of the randomly chosen quantum circuit. Okay, and then the second thing is we can only afford to take a small, like think polynomial, number of samples from the quantum device. So we want the sample complexity of this test to be efficient. Okay, we don't want to take more than polynomial number of samples. Right? So these constraints are, well, quite constraining. And so to get over this, we have a compromise. And this compromise makes sense in the intermediate scale era, but it probably does not make sense for a much larger than intermediate scale. Okay? And that's that it's okay to use exponential post-processing time on a supercomputer to compute a small number of ideal output probabilities. Okay? Now this is doable, for example, for n equal 49 qubits. Might be doable for 50 or 60 or 70, but at some point, of course, it's not going to be doable. Okay? Nonetheless, even with this compromise, this is still a very challenging goal. Okay? And that's because the complexity arguments that we just talked about require closeness and total variation distance from the ideal distribution. All right, but we cannot hope to unconditionally verify this using few samples from the device. Okay, there are actually property testing lower bounds that say that in general we'd need an exponential number of samples. Okay, so in addition to this compromise, we're going to need other compromises as well. Okay, and the question is which ones are we happy making? So we'll talk about that. Okay, good. Now let me describe the candidate test for verifying RCS. Well, the proposal is to compute the so-called cross entropy, okay, between the output distribution of the device and the ideal output distribution, right? And cross entropy is well named. It's exactly like entropy, except the probabilities come from the device distribution, pdev, and the log of the probabilities come from the ideal probability distribution. Okay, that comes from the circuit description. Okay, and of course this is just an expectation value, right, over the device distribution of log of 1 over the ideal probability. Okay, that's what this is. Now why do we like this? Well, it turns out that this can be well approximated in few samples using concentration of measure arguments. So let me tell you what we do. Right? To estimate this, what we do is we take k samples. For each sample, we'd use our supercomputer to compute the ideal probability of that sample, right, of that outcome. And then we'd take the logs and we'd average them. Okay? And then we'd accept if the score is sufficiently close to the expected ideal cross entropy, which can be calculated analytically. Okay? Because we understand what these ideal output distributions should look like with high probability over the choice of circuit. Good. So I just told you what we do. Now why do we do this? Why might this make sense? Well, so this is just some one-dimensional projection of observed data. Okay? It takes a whole bunch of samples and it maps it to a single number, like a score. Right? So it does not verify closeness and total variation distance directly. Okay? And in fact, we can make this rigorous. We can show that there exist distributions that score incredibly well on the cross-entropy test, but in fact are like maximally far in total variation distance. Okay, so why did Google think about this test? Well, at least implicitly, Google is kind of making they make an assumption, which it's not clear how much they believe, but they do say it nonetheless, which is that the output state of the device, rho dev, right, is a linear combination of the ideal state plus the maximally mixed state. Okay, so this is a very strong assumption, but not surprisingly, I think if you make it, then indeed achieving near perfect cross entropy certifies closeness and total variation distance. But to be honest, it's a bit like assuming supremacy to get quantum supremacy, which is kind of not what we want to do. So we actually thought about this quite a bit, and we think we have deeper reasons to believe in the cross entropy proposal, that it should work effectively under only less stringent error models. Okay, so here's the claim. Suppose we take our experimental samples and we score our cross entropy, again using our supercomputer, and we find that indeed the cross entropy of this device is close to ideal. But now let's also assume something. Remember, we had to make more compromises, so here's the compromise we're going to make. We're going to assume that errors in the device only increase the entropy of the distribution. In other words, that the entropy of the device distribution is greater than or equal to the entropy of the ideal distribution. Okay? Well, in that case, I claim that the output distribution is indeed close to ideal in total variation distance. So let me sketch let me say why this is important first before I sketch a proof. Why this is important is because this assumption would indeed follow from certain noise models. Like, for example, local depolarizing noise would have this behavior that would only increase entropy. But not from others, of course, right? There are plenty of error models for which this would not be the case. But the point is there are reasonable error models under which one might believe this. Okay, let me get to the proof now very quickly. It's a simple application of Pinsker's inequality, which upper bounds the total variation distance between two distributions by the square root of 1/2 times the KL divergence. The KL divergence can be conveniently written as the cross entropy minus the entropy of the device distribution. And so, using just basic algebra from here and our assumption about the entropies, if we find that the cross entropy is epsilon close to ideal, we've certified closeness in total variation distance to error root epsilon. Okay? So this is good because, again, closeness in total variation distance conveniently connects back to their complexity arguments, which we talked about in the first half of this talk. Okay, let me say a bit more about verification. So one really important property of random circuits is that the output distribution of RCS are what we call Porter-Thomas or exponentially distributed. What this means is very simple. It means if we look at the probability over the choice of circuit that any outcome probability, Px, is equal to Q over N, well, that's going to be e to the minus Q. Okay, I would call this an exponential distribution, but some people call it Porter-Thomas. I want to be really clear about this, though. It is true that this is what we'd expect in a random circuit sampling experiment, but this is not a signature of quantum effects. Okay, it's not a signature of quantumness. In fact, we show in our paper simple classical models that are effectively Poisson processes that reproduce exactly this distribution classically. Okay. One thing that is true, though, okay, that might be kind of closer to a signature of quantumness is that pairs of distributions that score highly on the cross-entropy test tend to share similar heavy outcomes, like above median probabilities. Outcomes that occur with above median probability in the distribution. And this intuition was sharpened by a recent proposal of Aronson and Chen called HOG, or heaviest output generation, in which they have a different score. It's related to cross entropy, but it's not the same. And it measures this property of heaviness directly. Okay? And they conjecture that scoring above some threshold is somehow intrinsically hard. Okay? Now, they can connect this to non-standard complexity assumptions, which I think are quite interesting. But as of yet, we don't know how to connect this to well-studied complexity assumptions, like, for example, that the pH does not collapse. Okay? So we still have, I think, stronger evidence that these sampling tasks are hard, like the ones I discussed in the first half of the talk. Okay, the last thing I'll say just in passing is that we can create a generalized measure which simultaneously verifies both cross entropy and HOG, which we call binned output generation, and is in some sense information theoretically optimal. Okay, if you want to learn more about this, you should read the paper. But I think this is interesting because it gives a new kind of a new type of score that instead of using a single number, actually it's kind of a multi-dimensional score, okay? And so somehow can only be better than these other scores. Let me conclude here. So two things. One, average case hardness gives evidence that circuit sampling is hard, or I should say random circuit sampling is hard, even for random circuits which exhibit kind of generic interference patterns. Right, and then for sufficiently small supremacy experiments, we can verify supremacy if we make strong enough assumptions about the device output distribution. For example, that the experiment only increases entropy. Okay, thanks a lot.
Thanks a lot, Bill. If there are any questions.
So experimentally, you're not going to be able to implement Haar random unitaries. So if you approximate them, do you have any, does your proof go through and do you know how well you have to approximate them to make it work?
Yeah, that's a really good question. In general, we do have some robustness here, right? And we hope that within the fidelities that we're expecting from these experiments, we will be able to just carry through all of the error into kind of a total variation distance. But doing exactly that math is something I think I have not done yet, so I don't want to be too confident about it. That's a good question.
Same question. Oh, cool.
Any other questions?
Yeah, so this is somewhat of a basic question, but where on your, or where in your proof on one slide did you use the assumption that the device distribution has larger entropy than the ideal distribution?
Oh, good. Yeah, let's go back to that. We did use it, but we went through it very quickly. Okay. So maybe let's go through it a bit more slowly. So let's see. So we had Pinsker's inequality, which upper bounded total variation distance by KL divergence, right? But now the KL divergence is defined in terms of the cross entropy minus the entropy of the device distribution, right? And now in the next step, we want to upper bound this by the cross entropy of the device, the cross entropy minus the entropy of the ideal distribution, so that we can then use our assumption, right? And that is where we have to use our the assumption that we made.
Okay, thanks.
Cool. We have time for maybe one more. Yeah, back there.
I feel like the anchor leg in a relay. How practical would it be to simulate boson sampling circuits on a standard digital computer?
Yeah, that's a good question. I think it's not so practical. So the truth is everything is polynomial, but the polynomials involved in those, I'm afraid, will be way too big. So I think it's much better. So I mean, that's a great question, because that's in fact theoretically something we could do in this model, right? We could just simulate boson sampling, but it's much more efficient to get it directly, because we're talking about very small numbers of qubits, and so n squared, n cubed blow up in qubits is really going to ruin the whole advantage for supremacy. But it's a great question, because we could, in principle, do that.
Cool. If there's no more question, let's thank Bill again.